Okay, hello everyone. I am Dr. Y. Padma Sai, Professor ECE, working for VIGNANA JYOTHI Institute of Engineering and Technology, and I am also serving as a chair, Student Activity Committee, IEEE Hyderabad section. Today we are going to discuss about fundamentals of signals and systems. So it is the one of the basic and a very important course for electronics engineers. So we are going to study basic signals. A signal is a physical quantity or a function that varies with one or more independent variables and carries information. So mathematically, we have two types of signals. One is continuous time signal, and the one is discrete time signal. When we are discussing about continuous time signal, it varies continuously with time. In discrete signal, the time index is n. Signals represent information such as sound, images, voice, temperature, ECG, EEG, and data, etc. So the great scientists, we have to discuss about them here. So after the invent of sampling theorem by these great scientists, so we are now enjoying all these digital facilities. So always will get doubt. Even in 1928 and 1949, we don't have anything like now we have. But these great scientists invented Shannon and Nyquist sampling theorem. After that, we are able to convert any continuous information into discrete by using sampling theorem that you are going to study in last unit of your signals and systems course. So for connection of these things, so sampling theorem is nothing but converting any continuous signal into discrete samples. So all communications, so what we have to do is instead of transmitting analog information, we are transmitting digital or discrete information. So by using sampling, we are converting any continuous time signal into discrete. After that, we are quantizing, converting into digital. That signal is transmitted by using transmitter. At the receiver side, once again, we are doing reconstruction. And so we are receiving that information. We'll study the sampling theorem in 5th unit clearly. Coming to continuous time signal, we are calling those signals as analog signals. So I already mentioned a continuous time signal is defined for every value of time. For example, so if you want to draw a diagram of any continuous signal, it is continuously varying with respect to t. Your x-axis is t and y-axis is x of t. The amplitude of the signal at that instant is, it takes infinite values whenever we are considering continuous time signal. So example for continuous time signal, you have n number of examples. My voice is also continuous. Temperature variation. Everyone is fond of cricket match. If you want to see cricket match, whenever you are observing the score from 10 to 20 overs or 0 to 20 overs, that time you will get continuous signal. And ECG and EEG signal, radio waves, etc. Characteristics of continuous time signal, I already mentioned, exists continuously over time. Amplitude can take infinite values, usually generated by natural or physical systems. Applications of continuous time signals, when you are capturing any signal by using sensor, so all are in continuous fashion. For analysis purpose, we are converting those signals into discrete or digital. So in many, we are having n number of applications. Here we are only mentioning few applications: biomedical signal processing, ECG monitoring, EEG analysis, EMG signal processing. Next one is communication systems, radio broadcasting, analog television, telephone systems, satellite communications, all those things comes under analog. Control systems, industrial automation, motor control systems, in instrumentation, temperature sensing, pressure measurement, audio and speech processing, microphone signals, music systems. Coming to discrete time signal. So already I have shown the diagram. Once again, I want to show it here. So now your time axis is n, signal is x of n. It is only, suppose if you are watching cricket match, I don't bother about the runs all the instant. I want to see first over or second over. So based on that one, whatever in that instant only will get information. Such type of signal we are calling as discrete time signals. Actually, at this level we are treating discrete and digital same, but in general, after getting your discrete time signal, after doing quantization process, you will get digital signal. So characteristics of discrete time signal exists only at discrete instants. I already mentioned. Suppose if you want to see, observe at instant 1, whatever amplitude. For example, it is having amplitude 2. Okay, so now at 0 also it is having amplitude 2. At 2, suppose if it is having amplitude 3. Even though you are having signal exists at different instants, but you want the instant 2. So you are observing signal at that instant, it is having amplitude 3. So okay, I already mentioned it is usually obtained by sampling of a continuous time signal. So you will get discrete signal. Okay, why we are going for discrete and digital? So actually when we are studying about analog communication and digital communication, during that time you are having a lot of difference why we are switching from analog to digital. So for one instant I will explain. Whenever we are using digital systems, it is easy to store and easy to retrieve. But whereas in analog systems it is very difficult to store and retrieve. And if you want to transmit signals also, you can transmit by using analog communication, you can transmit one signal at a time. But by using digital communication, you can transmit by using TDM technique, you can transmit many more signals in the same channel. So that is the beauty of digital communications. Okay, more noise resistant. Even though we are, while transmitting, you are having noise, by using channel coding techniques, you can detect the errors and correct the errors in digital communication. You don't have such a beauty in analog communications. Because of all these advantages, we are switching from analog to digital. So it is easy to process by using your computer or DSP processors. So for example, digital audio, sampled ECG signal, computer data, mobile communication signal, all these things comes under digital signal. So now applications of, only I have listed few applications of discrete time signals. We are using every field discrete time signals only. So if you want to process any signal by using DSP, so one of the applications, when you are capturing signal by using sensor, it is corrupted by noise. So we have to pre-process that signal. By using filtering technique, we are pre-processing signals. So next one is compression. Already all of you are familiar with why we are doing compression. We are having restricted bandwidth. We cannot transmit entire information. So because of that, generally we are doing compression at the transmitter side. At the receiver side, once again, we are decompressing or expanding the signal. Okay, next one is enhancement. So actually we are studying more enhancement in image processing. So when you are capturing the signal, if it is corrupted by noise, we are removing noise. So the clarity is not good. During that time, we are using enhancement technique. Next one is biomedical signals or biomedical applications. In biomedical applications in various fields, when you are capturing ECG signal or EEG signal, so based on the signal characteristics, we are deciding whether the person is having problem or not. So I have done my PhD in epilepsy detection. I worked with NIMS doctors. During that time, I have taken data EEG. Based on that information spike count, I am able to decide whether that person is having epilepsy or not. Like that, each and every field we are having n number of applications. Similarly, communications, image and video processing, artificial intelligence and machine learning, and embedded systems. So we are using discrete time signals everywhere. So difference between continuous and discrete time signals already we have discussed. So we are representing continuous time signal as x of t, discrete time signal as xn. So it is a time variable is continuous, whereas in discrete it is discrete. So we are processing by using analog circuits, whereas in digital signals we are processing by using DSP or computers. I already mentioned it is difficult to store and retrieve the information in continuous time case, whereas in digital it is very easy to store and retrieve. Noise immunity is less. Here it is more. Even though we are having noise more, we are having different techniques are available. Easy to remove noise in digital case. Accuracy is moderate. Accuracy is high. Example ECG and audio. When you are capturing any real-time signal, all are in continuous domain only. For processing those signals, we are converting into digital. Next one is importance of signals. Signals are fundamentals in many of the domains. So communications, healthcare, artificial intelligence, robotics, embedded systems, image processing, automation, wireless networks, data analytics, smart systems. So when you're processing, suppose if you're capturing any information from any human being, for example, if you want to test whether that person is having heart problem or not, during that case, what we are doing is we are capturing ECG signal. After capturing that signal, it is continuous. So we are converting that signal into digital for analysis purpose, and the same signal we are monitoring and controlling. So based on that, we are making decisions after applying some AI and machine learning algorithms for the data, whatever we are capturing. So we are giving some information to doctors instead of spending their valuable time for a lot of time. So we are having a lot of scope in healthcare. So next one is, so before going in depth of signals and systems, it is our responsibility to know the basic signals. So first one is, first we discuss about all continuous time signals. The same thing, same signals will appear for discrete time signals also. We start with unit step function. Unit step already it is, here it is defined. U of t, generally we are calling unit step signal as U of t. It is equal to 1 for t greater than or equal to 0. It is equal to 0 for t less than 0. So it is defined like that. Okay, and it is having amplitude as unit. Because of that, we are calling that signal as unit step signal. So next signal is unit impulse function. Sometimes if you refer books, sometimes they are calling unit impulse signal or unit impulse function. Both are one and the same. Okay, it is defined as delta t. Delta t is equal to 1 when t equal to 0. Otherwise, its value is 0. Already it is defined. When you are integrating delta t, you will get step signal, or if you differentiate step signal, you will get impulse function. Next one is ramp signal. Ramp signal is R of t. R of t is equal to t. It is continuously varying from 0 to, as t is increasing, its value also increasing. So if you differentiate R of t, you will get step signal. Area under ramp signal is unity. Next signal is parabolic signal. Parabolic signal is defined as t square. Generally, we will call parabolic signal as t square. If you differentiate parabolic signal, you will get ramp. If you double integrate once again, you will get u of t. So u of t equal to d square x of t by dt square. That is step signal. After differentiating twice parabolic signal, you will get step signal. If you differentiate one time, you will get ramp signal. Next one is signum function. Signum function is defined as sgn of t. It is having value 1 from 0 to infinite, having amplitude 1. For negative values, it is from 0 to infinite, it is having minus 1. It is defined like that. Signum of minus t is equal to minus of signum of t. Sometimes this signal we are calling as odd signal. We will see what is meant by odd and what is meant by even after next few slides. So that signal is discontinuous at t equal to 0. So we can relate a signum function and step function. Signum of t equal to 2u of t minus 1. Exponential signal. So exponential x of t equal to e power alpha t. If alpha equal to 0, it is constant. Signal is constant. It is having existing from minus infinite to infinite, having amplitude 1. Whereas for alpha, based on your alpha value, so sometimes if alpha is greater than 0, exponentially increasing or exponentially rising signal. If alpha is less than 0, decaying exponential. So now coming to rectangular continuous time signal. So here x of t equal to a rect of rect of t by tau. So where a is amplitude of the signal, t is pulse width or time duration. A rectangular function we are defining as rect of rectangular function. Here I have given one example. In this case, x of t equal to 4 rectangular of t. So now this is a periodic signal. It is having amplitude of 4 units, amplitude 4, and it is existing from minus 3 to 3. It is even signal. Okay, so this we are defining as x of t. This is a rectangular pulse. The signal is mostly used in pulse communication systems, radar systems, sampling and switching circuits, digital transmission systems, and all signal processing applications also we are using rectangular pulse. Next one is triangular continuous time signal. So it is defined as x of t equal to a into 1 minus mod t by capital T. Mod t is absolute value of time. T is the time duration. For example, this signal also even signal. For example, if you are considering x of t, so this is, for example, I am having it is having amplitude 3, okay, and minus 2 to 2. This one we are calling, actually in this case we are considering period S5, but here I am during that case what happened, I will arise and explain here. So once again, in this case I have considered my period as 5, t equal to 5. So because of that, so this is, your signal is existing from 5 to 5. This is time axis as t, and amplitude is, didn't mention any amplitude, because of that amplitude is only a. This we are calling as triangular continuous time signal. Okay, I already mentioned it is having maximum value at t equal to 0. This is 0 axis, and it is having amplitude a in this case, and signal decreases linearly on both sides. So because of that we are calling this signal as a symmetric signal. Whenever it is symmetric, we call that signal as even signal. Now coming to sinusoidal signal. Sinusoidal signal already you studied in your intermediate 2. X of t equal to a cos omega naught plus or minus phi, or a sin omega naught plus or minus pi. So where capital T equal to fundamental period, that is 2 pi by omega naught. Okay, so now here we are having two more signals, sync pulse or sync function or sampling function. These also, when we are studying signals and systems, you come across these signals. SC of t equal to sin t by t, and it is existing at it is equal to 0 for t equal to plus or minus pi, plus or minus 2 pi, etc. That signal we are calling as sampling function. Similarly, here we are having a signal sin pi t by pi t. That one we are calling as sync function. Already you studied in your mathematics 2. It is also having amplitude 0 at some instants, plus or minus 1, plus or minus 2, etc. So next one, up to now we discussed about continuous time signals. Now we are switching to discrete time signals. So similarly here also delta n, first impulse function. Impulse is defined n x delta n. I already mentioned the same thing here also. It is having value 1 at n equal to 0, and remaining all other values it is having value as 0. So this signal we are calling as impulse signal or impulse function, both are one and the same. And coming to next signal, step signal. Step signal here we are calling as same notation, only difference is in continuous time we are calling that as u of t, here we are calling as u of n. It is having values 1 from 0 to infinite. It is having value, a magnitude of that signal is only 1, and it is having 0 for all negative values of n. So u of t is defined, u of n equal to 1 for n greater than or equal to 0. It is 0 for n less than 1. So next one is, we can use step signal in switching operations, signal activations, and impulse function is used in signal analysis, convolution, finding impulse response of a system. During that case we are using impulse signal. Next one is ramp signal. Ramp signal is defined here also, we are calling ramp as R of n. R of n, this is n. At 0 it is having 0, at 1 it is having 1, at 2 it is having 2, at 3 it is having 3. That is R of n is n into u of n. Okay, we are calling that signal as ramp signal, and this applications of ramp signal is modeling gradual increase, system testing. During that case we are using ramp signal. Next one is exponential signal. Exponential signal is x of n equal to a power n. If a is less than, mod a is less than 1, decaying exponential. If mod a is greater than 1, growing exponential. For example, x of n is 0.5 whole power n. So that is one of the example of exponential signal. So this also we are using in system response analysis, digital filtering, we are using exponential signals. Next one is sinusoidal signals. x of n equal to a sin omega n plus phi, or x of n equal to a cos omega n plus phi. So all sinusoidal signals are used in analog communications as well as in digital communication as carrier signal. Okay. So now A is the amplitude of the signal, omega is the angular frequency, phi is phase. So I already mentioned applications in communication systems, audio processing, sinusoidal signals are used. And random signals. A random signal is continuously varying with respect to time. Such type of signals we are calling as random. So this is used in noise modeling, communication analysis. Signum function, next one is signum function. Signum of n is 1 for n greater than 0. It is 0 at n equal to 0. And it is having value 1 for n less than 0. Signal polarity direction, during that case we are using signum function. Similarly, rectangular pulse signal. Rectangular pulse, here also we are having, it is having value 1. Suppose if you are considering some duration of your rectangular pulse, in this case, for example, if you assume minus 5 to 5, okay, it is having amplitude 1. So what happened? It is having, so here I am not mentioning all those points. So your signal is existing from, okay, 1, and it is duration of the signal is from minus 5 to 5. Such signal we are calling as rectangular pulse signal. So this also used in pulse generation and digital transmission. Rectangular pulse is used. So now I already mentioned only difference between continuous and discrete. In continuous case we are using time axis as t. In discrete case we are using time axis as n. So only in here signal exists only at discrete time instants, whereas in continuous case your signal exists all the time. Usually discrete signal is processed by using either computer or DSP or microprocessor. So I thank and all of you, and I acknowledge, and references followed. I followed most of the books which are listed here. So I always feel by reading those books, even though they don't have anything now what we have, they written those books nicely for easy understanding. In BPLATI, I like BPLATI very much compared to all for introduction chapters. Switching from vector to signal, signal to n-dimensional, afterwards Fourier transform, Fourier series to Fourier transform, all those switching nicely explained in BPLATI. And one of the book that also Phillips, I like that. So how Fourier mentioned switching from Fourier series to Fourier transform, how four scientists discussed about Fourier paper, all those things nicely explained in that book. So I request all the students try to read standard books and learn well. Thank you all.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.